Hello everyone, Tim Nguyen here. So for those who have been following me, you'll know that I've been making some solo math lectures on YouTube. Today I'd like to try something a bit different, which is to make collaborative videos. So what that means is that I'll be bringing on some external expert guest, and together we'll be discussing technical material over a virtual whiteboard. So I think this is a good idea because right now there are lots of audio-based podcasts for discussing scientific material of various sorts, but few of them incorporate the visual technical elements of a scientific discussion, writing equations and the like. And so I think this is a good idea to try this virtual whiteboard format, since not only is it a good way for me to learn things from world-class experts, but also because it will be good for audiences that want to dive deep into the technical details. And so to kick things off, today my first guest will be a longtime friend and former college classmate, Po-Shen Loh, who will discuss the mathematics behind his novel approach to fighting the COVID pandemic.
All right, everyone. Well, we're very happy to have Po with us today. So Po and I go way back to Caltech. We were both classmates there. And well, now Po has gone on to do many great things. Let me just say a few things. So Po is a math professor at Carnegie Mellon University. He's also a coach for the US International Math Olympiad team. So for those who don't know, that's a competition every year where the world's brightest math high school students go compete in solving a set of math problems that are very challenging. Po is also a social entrepreneur in that he has started two companies where he's been able to leverage his mathematical skills. The first is XP, which is focused on math education. And the second is a novel app called NOVID, which is the world's first contact tracing app, which is mathematically grounded. And that's what we'll be focusing on today. Po, did you want to add anything to that?
Oh my gosh, it's wonderful to see you again. Actually, weren't we living like next to each other with just a laundry room in between? Is that what it was?
I was going to mention that, but vertically next, because you were one floor down, exactly.
That's
on the second floor, you were on the first floor, and I was just up the staircase.
Got it, because I remember seeing you all the time. So to me, it's like you look the same as you did before, and it's just wonderful to be able to reconnect.
Yeah, you too. You look exactly the same. Yeah, great. Yeah, so I'm really glad we're reconnecting and talking math. Both of us having studied math, and it's great to sync up again. And you've gone on to do math in so many different ways. You know, I was an academic mathematician. I still do mathematical things now as a machine learning researcher. But anyways, so we're still mathy people in different ways. But that's good.
Absolutely.
Awesome. So as I've explained to others, I thought what I do in this podcast format is to get a chance to go deep into the math, say, because usually when you just talk about things, either in a public lecture or in a news article, you obviously can't write equations or say anything too technical. And on the other end of the spectrum, if you write a technical paper, most people don't have the time and energy to slog through it. So I thought maybe we could combine the social aspects of podcasting with the technical aspects of writing on a whiteboard. So here we are.
Yeah, that's a brilliant idea. Happy to try this.
Okay, great. So the first thing, do you want to start off by saying anything about NOVID, or should we just dive right in? I mean, I have the screenshot of, I guess, what it looks like when it pops up, but maybe people don't even know exactly what it's supposed to do yet. So maybe you could explain at a high level what it is and maybe how or why you got started.
Yeah, absolutely. Actually, I think that the most important thing is, in fact, what's on this screenshot that you picked. You picked a pretty good one because it's all words right now. And I understand that we're going to go pretty technical, I guess, but it's nice that we start at least with something that anyone who comes across this podcast can understand, what the gist is of where we're going. And you see, it looks like a contact tracing app, but it says on this thing, a NOVID user 3 degrees of separation away from you just reported positive for COVID-19. And that's what's different about this concept of 3 degrees of separation. The area of research that I was working in for my pure mathematics research before was graph theory, network theory. And the concept is that whenever you have a bunch of nodes connected with some lines, this is something which is called a graph. I mean, it's not like the y equals x kind of graph that people are usually used to seeing in school. But when you have something like this, which is called a graph, then you can have a different notion of what distance means. And so what we did is we said, well, you see, when you're thinking about how to control a disease, right? Suppose that there's a sick person here. I'll use this red stick figure to say that that person is sick. So normally when you think about trying to control a disease, the way that everyone was doing this before is they said, find the people who are sick, find out who has been too close to them, and then try to remove them from the rest of the society so they don't get anyone else sick. That was how everyone did it. And just, I think it's worth actually drawing the concept of what everyone was trying to do. Well, they were trying to remove all of these people. I drew some yellow X's, like you were trying to remove people from the society. And
sorry, you're removing the sick person or the neighbors of the sick person?
That's very good. You're right. You better remove the sick person too. I forgot. I think I forgot the sick person. But yeah, thanks. Good. That's cool. So you need to remove all of these people because they're dangerous. And actually, yeah, the sick person is the most dangerous one. But the reason why I'm emphasizing this right now is because unfortunately, you're kind of asking people to be removed against their natural incentive. It's not really like you remove them so that they can be healthier. It's you remove them so that they don't get anyone else sick in the event that they were sick before. So that was what everyone was doing before. And because of these game theoretic or incentive alignment problems, well, people didn't necessarily want to go along. There we go. I just cleared out those X's. Now, what we did is we said, what if you instead recognize that there's more of a graph out here, more of a network? And I want to emphasize that in what we did, we actually defined an edge, a connection in the network, one of these lines. Each of these connections meant that the two people frequently spend time nearby. So this has some key things inside it. One of them is frequently. And that's different, by the way, from what people were doing before, because people were just saying, if there was somebody who was around the sick person even once during this period of contagion for at least 15 minutes, remove them. And what we said is let's make our graph have connections where it's based on who is frequently around them. Our frequently means like there's multiple days in a 2-week period. This is one of the differences between what we were doing and what everyone else was doing. And then the interesting thing becomes, well, suppose there's you somewhere. Maybe this is you. I'll draw a green for you. Now, in graph theory, there's the notion of how far apart two nodes are, two vertices are. Sorry, I'm slipping. I'm using the mathematical words as opposed to the computer science ones. So these are usually called vertices and edges. And you can talk about the distance between any two vertices by counting the number of edges on the shortest path that goes between them. And so in this example, there are 1, 2, 3 edges. So the graph theoretic distance between you and the sick person here is 3. And our key insight was, well, instead of just trying to grab all the people that were around the sick person and try to remove them from society, instead, just tell everyone whenever there's a new sick reported, a new sickness, a new infection reported, tell everyone how many degrees of separation there are between them and that sick person.
By the way, just to clarify, so you, maybe you're going to go about explain this later, but you said the adjacency is based on the frequency of time spent. So can you say a little more about that? So in other words, am I only connected to you, say, Po, if I've been around you, say, in the same room for at least 5 minutes, or what's the threshold?
Oh, great. Thanks for asking. So let me just actually explain exactly what we are using right now in our threshold. So right now our threshold, I'll just write over here, threshold. Right now our threshold, I'm going to write down something that looks like it has a lot of arbitrary numbers in it, but it will be interesting that it's pretty robust. What we use right now is over the last 14 days, there are at least 2 days, 2 distinct days, where you were within 5 meters for at least 15 minutes.
Wow, that's a pretty, that's a somewhat involved definition. Yes. How did you arrive at that notion? Okay.
Yeah. Let's talk about that, right? So the reason, by the way, why I even bothered to write this down is because, as mathematicians, I think it was maybe one of our professors who once said this. It's like you can define anything you want. Definitions are not the proofs, right? But the importance is if you come up with a really good definition, well, then you can start making all kinds of deductions from it. And
Right.
I'll already apologize. Anyone here who was looking for deep math, you're not going to find it. Tim will have to interview a more sophisticated, deep, pure mathematician.
No, I think this is good. I don't think fighting the pandemic is about coming up with necessarily complicated math. It's about thinking clearly, and of course, part of thinking clearly is forming the right definition. So I think it's very valuable this is all just as valuable or more valuable than doing advanced math. But anyways.
Cool.
Yeah.
Okay, right. Yeah. But then continuing on to that philosophy, right? So the game becomes okay, why in the world does this definition look this way? Let's parse it apart. I actually claim that the most important parts of this definition are the over last 14 days and the at least 2 days. Because that's what removes the two people who ran into each other in the subway and you'll never see each other again. Now, actually, if you think about your own life, I'm kind of curious. You don't have to say any names, but given this definition, what kinds of people qualify for this for you in your own life? How would you describe them?
Yeah, when you say 2 days, you mean at least 2 instances on distinct days. Is that what you mean? Okay.
Not two continuous days. Days are 24-hour periods.
Yeah.
So I'm talking about 14 disjoint 24-hour periods.
I see.
And I'm saying there are at least 2 of them.
So what if you had, I don't know, 10 run-ins on one day? That won't count.
Nope, doesn't count.
Okay. I see.
Yeah. So in your life, what would that capture?
Yeah, let's see. Well, back pre-COVID, certainly your coworkers, right?
Yeah.
Certainly anyone you live with.
Yeah.
And anyone you see on the weekends more than a single weekend, or at least both days on the weekend, let's say.
So you've already figured out why it was 14. It's because some people have lives which include certain things mod 7. Like maybe every Saturday they go and play tennis with so and so, or like they always go and have lunch every Sunday with their mom or something like that. You know what I mean?
Right.
But the important thing is what you've just described are all the people who are very relevant to you, for whom you would be likely to see them again in the future.
Right.
Does that make sense? My point, by the way, is we are actually using all of the data that's collected, which is past data, to predict future interactions. And that's the difference between this definition and just saying you were within 2 meters for at least 15 minutes.
Right. That's too noisy, because if you go to a Starbucks, everyone in the store basically is going to be your neighbor now, right?
Yes. And that's not going to give you any useful information for how you should act. If one of those people was sick, it's well, am I going to see them? Sorry. It's not that one of those was sick. If one of those were sick, oh no, that's bad news. But the point of our system is to give you an actionable warning, like what you saw on that notification, which was there's somebody 3 degrees of separation from you in this network who just got stricken with this disease. The reason why this is now actionable is if you imagine that imagine the disease was actually much more lethal than COVID. Imagine it killed 1/3 of the people. Called I don't want to get that. Even people our age, if we had 1/3 chance of dying, and we find out that 3 of these kinds of degrees of separation away from me, this person has gotten stricken with a 30% lethal contagious disease, the immediate note to self is stop the normal frequent behaviors, because if I continue the frequent behaviors, I'm probably going to run into someone that's going to carry the disease to me. It's actionable. And it's not too noisy.
Yeah, I'm trying to think. I guess I think there's several things going here. So I think, for example, this metric might be adjusted depending on the deadliness of the virus in question, right? So, for example, if it were very, very lethal, you would want to know if you were in a Starbucks with anybody who had the disease, right? And then it's sort of you would only say need 1 instance of being close as your threshold. Is that right, or am I not thinking about it correctly?
Well, no. So what you just said is true in the sense that if it's very lethal, you'd be like, oh man, that is big deal. But unfortunately, game theoretically, that's not going to help you. What I'm trying to say is that our tool is the one that's designed for self-interest. If there's this very lethal disease and someone's telling you, hey, you got it already, oh man, it's okay, now what? Now what should I do? I guess I should try to save everyone else around me and like spend the rest of my one last week to live in my basement, right?
Okay.
If you actually think about it, like, are people that nice? If somebody found out it might be the last week of your life, please stay in your basement for the last week of your life. I don't actually know that human nature would make everyone be like, yes, I will now sacrifice myself in my basement.
Right, right. They might just go on vacation and enjoy their week and like, okay, who cares about anybody else, right? I mean,
Yeah.
no judgment, but I'm just saying that's easily within the bounds of what some people will do, right?
Yes. And so that's why I'm saying like the old-fashioned way of just saying tell the people after they are already around the sickness actually has a very strange and perverse reversal of how they might act in the more lethal situation. Because they might just be like, let's live it like it's my last week of my life. Darn it, I'm going. So now the reason why ours is different is because by the time you get that notification, it's like, oh man, I'm screwed. Your goal is to not get that notification that it's one away. Our goal is to give you actionable information of like, whoa, this new horrible disease has struck 7 degrees of separation from me. Okay, that's far. I'm gonna like keep doing my thing because I need to survive. I need to buy food. I need to work. And then you see it. Oh, it struck 6 away. 5, 4.
I see.
Then you're like, it's 3. Nobody's gonna get me to work. I'm done.
Actually, what's the first number you get notified by? Because I think 7's quite large. I don't think anyone would take that seriously. Because right, there's that well-known fact that you're 6 degrees of freedom away from anyone. So I think 7, you're already that might not be that informative.
Oh, so actually, by the way, now that's tying back to how this like funny definition is. Based on our definition, you're not 6 degrees of separation from everyone. In fact, this is a really tight one.
That's right. They're right. You're right.
So that's why I went into this, like talking about the use case, because that's explaining why we had these weird numbers that we put in. You see, it's because actually there aren't that many people 6 or 7 degrees of separation from you. From you, you're probably not going to get that far. Like from you to me, like you.
Right. According to this definition, because it requires proximity. Right.
Yeah.
So, right. Yeah.
Like we might even be like 100 away.
That's right.
I'm just trying to like think to myself. It's like I teach at a university.
Right, because we're across the country. Yeah.
Yes. Yeah. So it's actually got geometry.
That's right. Yeah.
Yeah. So sorry, I geeked out. I said it's actually got geometry because like you actually work on that stuff. But but like the thing is like well at this point the reason it's actionable and the reason why it's actionable is like each one of these things matters. And in fact, as the reason why we tell you all the way out to 12 away. It's psychological. It's because on the screen, we don't only send you notifications as text. We also show you some like histogram or bar chart. We show you a bar chart of like, here's how many new people got hit. You really should start to be scared at 3. And that's because at 3, if somebody just got diagnosed positive, they might already have infected someone at 2. Do you know what I mean? There might be a contagious 2 walking around, and maybe the 1 doesn't act fast enough to not get sick, and then you're going to run into the 1. So I'm like, 3 is the danger zone, right? But psychologically, if your display only tells people from 4 away, people are like, oh, well, it just appeared on the horizon. So we show them at 12 away, so they see this like wall of like red signals. And then by the time it gets to the 3, it's like, oh man, it's like 3/4 of my display is red. The zombies are everywhere, or something like this.
Okay.
But I want to tie back now to like the reason I gave this long thing was like this is where the numbers come in. It's like, okay, the most important thing in my definition was at least 2 days. That was it. Because if you change 2 days to 3 days, it's still quite close. You'll just miss the like your great aunt that you see every Sunday. But like you'll get your coworkers, you'll get your classmates. So, but if you change 2 days to 1 day, it becomes unactionable. What I'm trying to say is the actionability of this warning is completely lost when you change from 2 days to 1 day, because at 1 day, it's like I took the BART, and it's like, well, I'm connected to everyone in San Francisco within a short distance. But even if one of them got sick, it's not like it's not as actionable as telling me, stop your normal frequent interactions because on that backbone, there's a disease transmitting. You know what I mean? And then the other part, 5 meters, 15 minutes. You can change those. If you change 5 meters to 10 minutes, 15 minutes to 30 minutes, what you just described, your network is basically the same one. It's actually pretty robust.
I see. Okay. In terms of, for example, in machine learning, where I work now, often one needs to tune parameters. And actually any kind of statistical models, you usually need to tune parameters. So did you actually try 1 and 3 and found that those weren't good and then two worked well? Or did you just kind of like reason in your armchair, so to speak, and it actually just worked out well that 2 was good?
Oh, I make no claims to have come up with brilliant ideas from the get-go. We wandered around, right? So we started out with one day, and that was actually still useful at the beginning when we were building our thing. And then after a while, when it started to be tested out at a university like Carnegie Mellon, well, we found out that everyone was really connected. You know, like if you actually have people at a university campus using this, and one day is the threshold, you're like, everyone is pretty tight. So then we were like, aha, this is where we need to switch and make it more robust and make it 2 days. And then we never needed to make it 3 because at 2 days it was already meaningful. Anyone who was using it was already connected together in some way, maybe at longer distances, they spread out. And then this thing about the 5 meters, we started out at 10 meters. And then we found out that at 10 meters, due to the idiosyncrasies of Bluetooth, we were like having people in different apartments connected to each other because Bluetooth signals go through walls.
Ah, okay.
But once we dropped it to 5 meters, it also managed to make it so the wall attenuation or reflection made it so we didn't have to worry about like between walls.
Okay, nice, nice. You defined this, came up with this very good definition of adjacency, right, based on this threshold. So, yeah. So what's next? So yeah, what's next?
Right. So when we came up with this, actually, we didn't expect it to be that interesting. Honestly, we were just like, oh, we can do it. Because I'm a graph theorist. And I was like, let's go and collect the graph and do something interesting with it and try to make some algorithm to let people see on their app, like how far away these various sick things have struck. And it was only after having this and staring at it for maybe a week or a couple of weeks that we realized, oh, once you do this, then the game theory kicks in. Because you see, before when people were having other apps, the problem was number one, people didn't want to install the apps. People were like, my privacy is more important than this thing to track me. And then there were other things of when the existing apps that already exist, when people were notified by those apps, hey, you were around someone sick. And we promise you for privacy that no one will ever know that you were just told to stay home. Guess what people did? A lot of them just said, okay, I guess nice that you told me I'm dangerous to other people, but I'm still going to do what I'm doing anyway. Thanks for promising that no one will know I was just told. What I'm trying to say is that, you know, like if you think about it, the original paradigm of saying for every sick person, tell all the people around them that you now need to stay home and not get anyone else sick. Scout's honor, and no one's ever going to know that you were told to do this. Unfortunately, people then just don't do it. So there were like two fundamental problems with how this whole thing was done before. A, a lot of people didn't want it. They didn't see what's in it for them. And the number two, when it finally told them with this great privacy promise to do something that they didn't want to do, a lot of people just didn't do it. But now this is where this becomes very interesting. Based on this definition, and based on the concept that whenever there's a sick thing, let you know how many degrees of separation away, now let's do a thought experiment. Suppose that there is this lethal disease that kills 30% of people. Well, this thing has something in it for you. It's not just to like make sure you don't kill other people by accident after you got sick. It's like, this is how you don't get sick. So that actually has a powerful driver.
Yeah, I'm trying to think. So going back to the incentive structure. So how do I say? In both, okay, so like for example, the first thing you draw, I should start maybe writing on this thing myself. And the first thing you draw, right, you had this sick person, right? And then the default thing was to remove the neighbors of the sick node, right? So you would use a different color here. So you would, right? You would remove, say, you would tell these neighbors to quarantine, right? The one in green.
Yes.
Right. Now, what seems to be the same in both cases is that you don't. The neighbors don't necessarily know. We don't know whether they've been infected. We just know that
Yes.
they're distance 1 away from the sick person. Likewise, in your formulation, if you're distance 3 or whatever, you also don't know if you're sick yet. You just know what the separation is.
Actually,
right?
You hope that you're not sick.
But you hope that you're not
ours,
sick.
we're like, you better not be sick. That's the concept.
So I guess what I'm trying to say is, so in your case, the incentive is for presumably a healthy person doesn't want to get sick, and therefore they voluntarily quarantine, right?
Yes. Just think of what you would do.
Right. I'm trying. How do I say? Is the difference that in the original case, there's an external entity that's forcing you to quarantine, how do I say it? What I'm trying to say is I feel like what's common still about these two things is that there still needs to be goodwill and elective kind of integrity to say, okay, I might be sick or I might be near someone who's sick, so I should quarantine myself. Is the difference that in the first case, somebody had to force you and now you're hoping that the person will voluntarily remove themselves? Because even with the NOVID situation, like, you know, they still have to voluntarily choose to isolate themselves, right? So there's still a voluntary aspect to both situations. I'm trying to,
you're right.
The difference,
So both of them have a voluntary aspect. Like, that's actually the interesting thing. They both have a voluntary aspect, but in the NOVID thing, it is in your direct interest to isolate because you're still healthy and you want to stay that way.
Mm-hmm.
The point is, let's think again about this like thought experiment. It's like there's this new disease that's killing 1/3 of the people who get it. You decide that you want the app because you want to stay alive. You watch on your app that the disease is striking from far away to closer and closer and closer. What would you actually do? Like, you know, like this is like a radar on an aircraft carrier in the middle of the ocean. You see these blips, they're coming closer and closer and closer. What do? You enact defensive measures because it looks like it's coming into you. It's not like you wait until the bomb has gone into your deck and you're like, oh yeah, we're screwed. Let's quick sink the ship so that it doesn't blow up everyone else. Does this make sense? I'm like that's like a military analogy. The military analogy is like, I have a huge ammunition like stockpile in my ship.
Right.
Wait until after you're bombed to be like, oh, I better intentionally sink my ship now so it doesn't blow up my nearby ships. Or would you rather have the radar to be like, there's planes coming.
Right.
Take evasive action now. And that way there will be no bomb going into my ship. That's the point.
How I say. So okay, let's go back to the original case, right? I'm 1 degree away from someone who's sick. Now, either you can voluntarily remove yourself or an external entity can remove yourself. Is that the main difference, that now there's this external entity? Because
no, not quite. The main difference is that we have extended range. In ours, if it told you you were 1 away, you're already screwed. It's like we basically, the goal of everyone using our app is don't let it get 1 away, don't let it get to me. Mm-hmm. The goal on our app is that every report of how far away the new sickness is a large number. And when you see the numbers get too small, you take significant evasive action. So it never gets to 1 or 0.
Oh, okay. So I think maybe this is the point. So in the conventional setting, you're only notified when you're sort of too late because you're already 1 away. And there's kind of this, and then there's the second element, which is this draconian aspect of now you're going to be quarantined. I was trying to isolate that sort of draconian aspect from the math. So you're saying the point is, in the original system, it's binary. Either you don't get notified or you're notified at this very late stage. But
yes.
The thing is that your system, it's progressive. It's right. You get this large distance notification, and then it progressively can get smaller and smaller. And so basically you have more information and a longer time horizon on which to act. That's the main difference.
Well, that's one difference. But then the thing is, what do you do with that? So once you have the longer time horizon, you can take matters into your own hands. And the reason why you're quarantining has nothing to do with you being the dangerous one. It's about you being in danger and wanting to not get sick in the first place.
Right.
So yeah, it's basically, instead of a Boolean, true, false, were you too close or not? The binary, like we just tell you a positive integer, hopefully. 0 is bad. So okay.
I think we do that because for me, it seemed like there's always an aspect of human agency, no matter what mathematical structure you use, and that's technically decoupled from the math, because you could be in a world where everyone defects or everyone cooperates, and then the math wouldn't matter because everyone would just always do the same thing. But of course, we're not in that world. The difference is in the math, in that in the conventional setting, you just have sort of a one nearest neighbor information, whereas here you have the whole graph potentially.
That's right. Right. And then when you're talking about the defects versus cooperates, actually we designed ours in the United States under the hypothesis that everyone defects. So no, really, like this is why this is such a big deal.
Well, are you saying in other countries you observe different behavior?
Well, some countries have a very, very powerful government that will go and crack down on you, so then you can't defect.
Okay, I see. I can imagine some countries being much more cooperative. maybe, I don't know about at the level of countries, but certain societies might be more cooperative, right?
I will say, I talked to some government officials from a certain country I will not name, and I complimented them on how cooperative their people were. And that government official just told me, actually, it's not true. Our people are the same as every other people. We just have stronger rules and we enforce them. So that's what that person said. I won't say which country, but it was one that we would all think of as having very strong, very good control of COVID.
Okay, I could probably guess, but okay, sure.
It's okay, it doesn't matter. But what I'm trying to say is, like, actually, at the end of the day, it's great if it's actually great if people are cooperative, by the way. But the more robust solution is one which, even under the assumption of non-cooperative people, still works. Sure. And so that's why I gave this example of this, like, potentially really lethal pandemic. It's like, just think of how a normal person would act, even if they were just like looking out for themselves. They'll be like, oh, I got a radar. All right. So if I don't want to die, what do I do to not die?
Sure. By the way, so in the conventional, so now there's this technological aspect, because I'm wondering, for the conventional setup where you just know the one nearest neighbor, is it sort of these very simple notions like maybe your direct relatives, your coworkers, because you're using technology to compute these distances. In the conventional approach, how do they decide who to quarantine? Because there isn't an app, right? There's just some decree to quarantine.
Okay, so there are some people who do this manually. In some countries, the way this would work is that there would be professional contact tracers who would call you up and ask you who were you around, and that's a very manual process. Some countries use, like, your credit card purchases to figure out who else was buying stuff from the same place at the same time. And actually, even in the US, we had these voluntary apps. In fact, Google and Apple were making the backbone for this, right? And they were using Bluetooth. It was technological also. The only difference was that when they were doing this, they were only thinking of making an app for contact tracing. So this, like, manual process. So they were only thinking of notifying the nearby ones. What we did is we said, wait a second, what if instead of just making an app for the thing that people are doing, we think about what you could actually do with the smartphone? And that's how this new mechanism of telling you how many degrees of separation away, this is a uniquely 2020s possibility.
Is it just, how I say, is it an issue of having the right data structure and storing more data? Because I imagine once you've solved the problem of doing one nearest neighbors, you can sort of iterate that to get two nearest neighbors, right? So
it's trivial. Okay. So that's why I apologize. All you're getting here is trivial stuff. I made a trivial observation. The trivial observation was, given all the data that you're collecting, if you collect the data and do this with the data, you know that you have the same physical and electrical sensing, the same stuff going on. If you just define your graph differently to have at least 2 different days, so that you don't get too noisy data, right? That's one important piece. And the second piece is report the graph theoretic distance instead of only telling the binary you were around or not. If you just do that with all the technology you have, you suddenly unlock a game theoretic incentive-powered tool that could save the entire human race from the next catastrophic pandemic, powered by selfishness. That's what this is. It's trivial.
I'm trying to think about, okay, like, do you know, okay, so let's say Google, Apple, say, so you voluntarily submit information, right? So it's like, trying to think. Are you saying that Google and Apple could have trivially modified what they were doing to also make this graph too? They just didn't.
Yes.
Okay. Okay. I mean,
But I should also say there are reasons, by the way. Like one of the reasons is because of privacy. It's because actually at the very, very beginning, at least from my understanding of the history, around March of 2020, there were all these people clamoring to say, Google, Apple, you already know everything about where everyone is. Can you just go and use what you already have to just do this? And then Google and Apple said, we promise we don't actually know that much about everyone, so we'll make a special app that will keep everyone's privacy, which I think is actually still a little bit funny because my iPhone does seem to know where I am all the time. So it's just like whether or not like anyway, so it's like they could have done that. And I have a friend, I'll not say anything about my friend. Anyway, whatever. So it's just like all of these things like people could already tell. But at the very beginning, you see the only thing people were thinking of doing with that was just the contact tracing. And then the privacy experts started to say, you know what, why are we like getting all this information out? And then you're going to be using this to like control people, because that was the point of it. And so there was a lot of pressure to go and make a system that was like as not aggregating information as possible, which is ironic because the companies running it already aggregate information. But that's why that system was, it was like I don't want to call it politically charged, but it was ideologically charged to not do as much.
Interesting. Okay, so I think maybe this is the next interesting thing we can go into, because it sounds like, okay, on the one hand you said, okay, this is maybe a trivial mathematical modification, but of course in the real world things aren't as clean as math. There's the implementation, and that comes with all the problems of the real world. So you just mentioned now that the big tech giants had an issue of just kind of using all the data, so to speak, which they have plenty of. So how did you overcome that to implement NOVID without having to go through all those thorny issues?
I think that the first big thing is that we actually came through and explained that there's a reason why doing it this way is more advantageous, right? What I want to say is that in March 2020, actually nobody had this idea. In fact, I've never met anyone else in the planet who had come up with this idea and pushed it. I know this because I've been giving talks now at like various international conferences about this, and this appears to be, this trivial mathematical observation is one that was not made. And so actually what was going on early on is that in March, April, the spec for the Google and Apple system was already laid down. And as you know from working with a large tech company, once the spec is laid down and is scaled out to millions and billions of people, it's not super easy to change the spec.
So the spec of their contact tracing.
Yes.
Okay.
And the design, and what they've done a lot of effort to onboard the privacy community. They've onboarded governments. If you've already convinced some government that this is the way to go, it's very difficult to talk to that government again and say, hey, by the way, we want to change up what we're doing. You already have people who are on board. And so the difference is just one of large versus small. Here I am, I'm calling you from our office. It's a pretty small place. If we need to change our direction because we realized this new idea in June of 2020, we can. And that's what we did.
So, sorry. Are you saying there wasn't it wasn't so much that you did something, there wasn't something that you did something super smart to outsmart the tech giants, just that you're more nimble, and so they were already committed to something, and you just said, well, hey, it's just me and my team, we can just do whatever we want to do, and you just acted accordingly. Okay.
Yeah. I mean, like technologically, if they wanted to do what we're doing, they could do it way better. I mean, they could throw 10,000 engineers at this thing, and then it would implement it. They'd like sense all of the distances. But but actually, that's the value of having an ecosystem where there are lots of players. Because actually, if there are too few big players, then you won't have as much innovation. But it actually often is these small players who can experiment. And after experimenting for a while, then you occasionally stumble across something like this.
Awesome. But I remember you were going to tell me at some point that one mathematical aspect of this was how to find, if you give me a radius, how to find the number of nodes within that radius. Although in your setup so far, our graph uses the notion of distance, but there isn't a notion of radius in our graph. So maybe you could explain that aspect.
Yeah, so actually for this app, there's one particular aspect that's quite important called uptake. And the uptake is often something which is contagious. Actually, this is an app which is spreading like an infection across the same network that a real infection spreads. It's just that our infection is called uptake of the app. And once we realized that a very important part of the user experience is to show people whether or not there are other people around them who are using the tool. That's important. You've got to quantify the tool's value to a person. And the way we did that is instead of saying, here's how many people in your zip code, we would actually go and tell each person, here's how many other nodes, how many other vertices there are at each distance from you. That's a way of letting you know that there's other people using it. Because it's much better than to just tell you, hey, somewhere in Pennsylvania, there's like 1 million people using this. I don't know, are those around me or not? But what we do is we show you a little bar chart. We say like, here's you, one user. And then there's like 2 people that you're close to frequently. And then there's like 3 more people that those 2 people are close to. And there's 10 people. Does this make sense? You want to show people like this nice chart. And now making that chart is not totally trivial if you want to have it be performant. Because once you want to tell every single vertex how many other vertices there are at distances of 1, 2, 3, 4, up to 12, because that's the range we tell, that could be computationally heavy. Like if you weren't smart about it, what you might do is an all pairs shortest path. If you have
sure. So actually, Po, why don't we actually go into the details of making the neighbor search performant, as you said. So let's actually think about how you would do this naively just as a start, right? So if you were to just, let me just illustrate what's going on here. You have all these nodes in your graph, they're all people. And let's say this green one is you. To look at the distance between each node, you'd have to just manually go through each one, right? And just compute the distance. And since there are, say, n nodes, and you have to look at, well, n minus one other neighbors, which is just off from n by a constant, you roughly have an O of n squared complexity to compute all the neighbor distances, right? Now you're saying that you could do something a bit better than this.
Yeah. I mean, one thing I would say there, which is quite interesting, because you're the one who has the degree in geometry. So I find this very interesting that that's how you look at it. You're like, it's O of n squared, because for the green thing you've circled, and for another one of the blue things, if you were doing like normal geometric distance, that would be a constant time operation. But actually, in what we're doing, whenever we calculate those distances, we actually are calculating them with respect to the network, the graph. So in fact, actually, it's not even necessarily constant time to go and figure out how far apart two particular vertices are.
I see.
You can't just plug into the distance formula.
I see. I think what you're saying is this. So if you had the distance, say, between 2 points, let's call it x and y, right? This would be in d-dimensional space, the square root of the distance of the respective coordinates, right? So this is an O of D computation where D is the dimension, right? So
right, and that's a constant for you.
Yeah. So if this is a segment connecting these two, you just compute that distance. But I guess what you're saying is that that's not the way you would do it. You would have to actually follow some kind of path to get there, and that requires, in principle, a traversal of the entire graph. Is that right? So is that an O of n?
So it's complicated. So actually, this is not the area I work in exactly, but I seem to remember there's some algorithm, maybe even named like Floyd-Warshall or something. But there was something about like an all pairs shortest paths algorithm, and these exist. I think all I'm saying is that this is not exactly my area of expertise, but it's at least O of n squared complexity. So you have this thing which is O of n squared, because for every pair you need to know the distances. Mm-hmm. And I'm saying, like, if you aren't careful, it might be O of n cubed, or it might be something serious. And if n is big, O of n squared, O of n cubed are both pretty painful.
Mm-hmm. Yeah, I guess the most naive algorithm, or the way to frame this problem, is compute for all pairs in a graph the distance between the two in the graph theoretic sense. And if you're in the worst possible case and you were unlucky, it could be as bad as O of n cubed, right? But you're saying there. Do you know what for a general graph with n nodes, what is the worst case scenario if you did the smartest thing?
Yeah. So that I actually don't know. That's a really interesting question. You need to ask somebody who knows more about that than I do.
Okay.
But, I will say that even just finding all pairs, like doing this all pairs thing, it's definitely at least O of n squared, because they're n squared pairs. And my issue is that even n squared is too painful if you want to build something for like n being a billion. The computer could do a billion calculations in like order of magnitude 1 second, but n squared would be like order of magnitude a billion seconds. That's a long time.
Yeah, that's right. Let's just summarize. So then kind of, we know that let's say let's call this the best algorithm. It's lower bounded by O of, well, actually, no, it's not. Sorry, we were still kind of, sorry, the O of n squared was already sort of the worst thing you could do, assuming constant lookup. But it's even possibly worse than that, because the lookup itself might be more expensive. So I shouldn't call this the best algorithm. It's sort of maybe let's call this how bad algorithm, how bad the algorithm can be, and it's at least O of n squared, but it's not going to be worse than O of n cubed. But it's still pretty bad looking. Yeah.
Right. Yeah. So I mean, the main thing that we had to do was to realize that since O of n squared is too expensive, are there other things we can do? And so one of the things is, if you look at it, O of n squared happens when you say I am doing something for like every pair. But if you think about what we were trying to do, we were trying to do something where for each user, they could see, here's how many people 1 away from me there are, how many people 2 away, how many people up to 12 away. And that won't be all 7 billion people on Earth. In fact, that won't be a massive number, but it could be like 100,000 or maybe even a million, like if you're in New York City or something. So actually, there's hope to do something like this, maybe in like a million times n instead of like n times n. And this has something to do with the way that even when you look at the entire world at once, you're not going to have to, like if you built this app to work in the United States and in Australia and in Europe and all of this, as you kept adding the n to get bigger and bigger, it wouldn't grow quadratically, because those the structure of human networks would make it so that even though you added some random people in these other countries, for the average person in Kansas, it doesn't make a single effect on them out to the distance 12 that they see.
Yeah, actually, I saw in your paper you mentioned the Watts-Strogatz work. I don't know if you want to say anything about that, but actually, let's just maybe make a new slide. So basically the point there is that, so let me just write the name. So there's this famous paper by Watts and Strogatz where they talk about this sort of small network or small world phenomenon, right?
Right.
And basically, one sort of takeaway from that is that you have this huge graph, but really it's a bunch of, say, these small clusters, and then there are these like maybe connectors that connect these clusters. Right, so you know, like maybe there's like a community, like one of these clusters would represent some kind of community, and then a connector would be someone who's famous or more popular, so because they know people from different communities, right? But the point you're trying to make is, as n grows up, gets larger, if the cluster size remains relatively constant, then really your algorithm is going to scale by that constant times n, which is much better.
Yes, which is much better, absolutely. Because the point is, like, even if for some reason people in Siberia started using the app, it makes no difference to me out to my distance of 12. I don't think I can get to Siberia, right? So this concept of this small world phenomenon, I think, is often described as like, let me draw a little brief picture here. The small world phenomenon is sort of like if I have a person, I'm drawing stick figures, but if I have these 3 people and like, both of them know the same common person, then the connection between these other 2 is more likely. More likely than typical. And that actually makes a lot of sense. If you think about the real world, if it's like I am frequently with someone and that person is frequently with someone else, the chance that I and that third person are frequently together, that's like more likely than just like me with some random person in Kazakhstan. So this is like, well, this has this small world phenomenon. And then what we decided to do to exploit this is we said, well, maybe since we know that we could sort of get it to be linear time, where that constant has to do with what these small worlds look like out to distance 12. Well, then we wanted to find ways to do that one more efficiently. And one of the things we also realized was that if you tell someone that there are exactly 52,237 people who are at distance 6 from them, well, it wouldn't be 6, it would be like distance like 11 from them, they don't actually care about all the digits of that number. Actually, if that number was off by like 10%, who cares? It's like if it was 52,000, 51,000, 53,000, it makes no difference. When you're seeing numbers close to you, if you find out there's like 3 people who are within distance 2 of you, you'd like to know it's 3 people. What I'm saying is that when the numbers are small, you do care that they're right. Once the numbers get big, a 10% error, who cares? And so this moves into the domain of something called approximation algorithms, which is also not something I'm a specialist in, but I know enough to be dangerous to myself. And so what we did is we actually put in a way to estimate these neighborhood sizes approximately. And when we do that, then we can get performance to be pretty darn fast.
So, okay, so these neighborhood sizes, are these neighborhood sizes, when do you compute them, or how do you store them?
Yeah, let's talk about this. This is actually kind of fun. So I'm going to go to the next screen just to get a clear, clear thing to draw on, right? So yeah, this is kind of fun. And I should say this was not my own idea. In fact, I worked on this with a brilliant high school student. It was a high school student at the time named Brandon Wang. And so as we were working on this, what I'm showing you is something that ended up being what we came up with together. And it's like, it's not rocket science. A professional computer scientist would come up with this in no time flat. But nevertheless, let me just explain it this way. suppose that you have a vertex, and I'm not drawing stick figures anymore. I've got this vertex, and I've got like all these other vertices which are directly adjacent to them, and it just keeps going. And this is a graph, so you might have like random things going all around. Anyway, I just drew all of these vertices. Okay, so I've got all these vertices. What I'd like to do is I'd like to calculate the number of vertices in every ball around every vertex with various radii. I say ball because you are a geometry person, so this would make sense, right? So if I'm talking about like the ball of radius r around vertex v, what I mean by this is the set of all vertices at distance, graph theoretic distance. I'm going to do closed balls less than or equal to r from v. Okay, so for example, b0 of v is just that vertex. b1 of v is the vertex plus the neighbors. And what we want to do is we want to estimate the sizes of all of these balls. So I'll start by saying, here's an algorithm you could use, and it will find all the ball sizes exactly, but it's going to be pretty inefficient. So the way that this algorithm works is, let me just try to write this down. Here's a bad algorithm. Bad algorithm. What you do first is you start with all of the B0, all balls of radius 0 of V. Well, that's just V. The balls are sets, right? So that's trivial. You can do that. And now you can imagine doing iteration. Iterate like 12 times because I care about 12 balls. What you do is that each time, so for each R, which goes from like, I don't know, 1 to 12. Here's my pseudocode attempt, right? From R1 to 12. What I feel like I'm doing a coding interview, programming interview. But what I do is I take for each vertex, well, I can let the ball of radius r at V. This is actually easy. This is a union of balls. It's the union of balls of radius r minus 1. So if I want to know what are all of the vertices within distance r from a vertex V, I can just take all of the vertices within distance r minus 1 of the neighbors of V. So I'm just going to write union of all of the neighbors, W adjacent to V, or W equals V, of the balls of the radius r minus 1, W. Does this make sense?
Oh, it makes sense, yeah, because basically what you're saying is that, let me just illustrate on your graph here, right? So here's U, and the only way you can go to, let's say if R is 2, so this would be R equals 2. The only way you can get there is to first go through a neighbor first, right? So you have to say, in this case, go to this vertex in the square that realizes, well, yeah, so this is in the R equals, yeah, I should have chosen a different number because they're both R equals 1 and 1, but okay. But basically by going to the neighbor, the R goes to R minus 1 once you go to neighbor, right? So you basically just sort of, it's an inductive problem where you reduce the R case to the R minus 1 by going to the neighbor.
Yes.
Right.
Yes, exactly. And then in my case, my balls are distance less than or equal to R, so I also union the BR minus 1 of the original V.
Right.
I think it helps to avoid some random edge cases that probably happen. But
sorry, can you repeat because this union, of course, is not disjoint, but that's an exact equality just by what I said.
Yeah, it's an exact equality. Hey, now I'm curious. Do I even need the W equals V? I just assumed I would need it. But looking at this, maybe I don't. Yeah, maybe I don't. I assumed I would need it for some edge case.
So, okay. Maybe you. Huh. Yeah, maybe you. No, I don't.
Oh, I do. No, I do for the case R equals 1. Because when R equals 1, if I do this, and I don't have if I don't include the W equals V, then I don't get the original guy in my ball of radius 1. So I'm imagining, like, suppose I have.
Oh, I see.
Yeah. I'm like, there's this edge case. I'm like, do I need to care?
But edge cases are important in mathematics and in programming, right?
That's true. That's true. But now that I'm looking at it, I'm like, maybe once R is bigger than 1, maybe I can drop the W equals V, but I don't care. It's like small enough. Yeah.
I see. But I think, the point is because the distance is less than or equal to R, you have to kind of have the V as just to
Yeah. Or else I have to prove some statement. I would have to prove some statement to be like, oh, also I can deal with the edge case. But anyway, so the thing is, I think this is true. What I wrote here is true. Maybe I can do better, but it's true.
Yeah, no, I think to prove what I just said, because it's less or equal to R, you don't necessarily have to go through the neighbor, right? You could just stay still.
That's right.
Right.
That's right.
So it's the inequality that demands that to induct, you don't necessarily have to visit your neighbor to reduce the distance. So I think it just follows from that.
Yeah.
Yeah.
Okay. Yeah. So what I wrote here, by the way, this would calculate all of these balls, and that's all you need to know how many things are at various distance, because that's like the take one ball minus another ball. If I want to know how many at distance exactly 7, it's the ball 7 minus the ball 6, right? Mm-hmm. But as written, this is a really lousy algorithm, because you're going to, well, actually, it's still linear time in the sense, it's linear time in the sense that if I only imagine that my neighborhood up to 12 vertices, up to 12 distance out is the same even as I scale my n to include random other countries in the world. Yes, that's true, but the constant can be kind of painful, because if I'm actually going to be taking unions, imagine what that ball of radius 12 is going to look like in New York. Like everyone's thing is they're going to carry like 1 million vertices in these sets. So the compute could take a long time if you actually were having each of the vertices carry around all these balls, and these balls were getting to be like million big, if that makes sense.
Yeah, let me just pause and think about this for a second here, because the set of neighbors isn't changing with respect to V.
That's
right?
Right.
The thing that's getting large is that the balls are getting larger, and I'm just trying to think about because for so I think for if you just fix the vertex V and didn't care about anything else, this wouldn't be so bad, because you just keep taking these successive unions. But the problem is that you want to compute this for all.
Yes.
Yeah.
Yes. Actually, what you just said is it's also parallelizable. So that was also important for us. You can parallelize this too. So what was important to us was like, well, suppose we got tons and tons of people using the app. Maybe we could even shard the data and have like the various pieces just do their compute, if that makes sense. But the fun thing is that you can, if you're willing to have this like little bit of error in the estimates, you can actually do something that makes this significantly faster. And the idea here was to borrow an idea from hashing. So So the idea is like, maybe I have a ginormous n. My n might be 1 billion. But what I will do is I will actually first make some hash function. So now let me adjust this a little bit. Let's make a hash function. So let me write on top. Suppose I have a hash function. Hash function means something with like, that looks pretty random, but it's like clearly defined. A hash function from the vertices 1 to up until n, that was our vertices. And it's going to spit out numbers for us, which is from 0, 1 to, I don't want that. I want ... 1023. That's a nice power of 2. So we have like 2 to the power of 10 options. So what we're going to do is we're actually not going to store B's. We're going to store, I'll call them C's, I guess. So let me define a new thing. So what I want to do here is I want to store CRs instead. And CRV is going to be the set of all F of, let's call them F of W's, for all the W's in the BRV. Okay, this is a mouthful. All I mean is like, I'm basically taking that BRV, which was a bunch of vertices, and I'm not going to store the vertices in my set. I'm actually going to store the hashed values of the vertices in my set. Now suddenly I will never drag around 1 million things in my set. I'm only going to drag around maximum 1024.
I see. So,
and the update is the same. The important thing is this, the update BRV is something, because of this definition, I'm basically just mapping everything through F. And so if I want to run the same algorithm, my iteration is just do the same with C's instead of with B's.
So actually, okay, first of all, the hashing makes this an approximate calculation, but also it caps the size of the number of neighbors to consider. Although, okay, what I was trying to say is your original point earlier about, okay, if you're 50,000, if you're off by 10%, who cares? Well, if it was 50,000, but you're capped at say 1,000, that's a really big difference, right? So
okay, you're right. You're right. So this is not the complete algorithm, and you've just pinned on something which is a horrible thing about this, which is like, hey, if you got to 50,000, you're going to be maxed out. It's going to be like there's 1,024, so you don't know anything. That's okay. We're going to do multiple resolutions of this. So what this does first, like this first thing, this first pass, it will still be meaningful for you if your C7V has like 700 things in it. If it does, that means that the true B7V doesn't have 700, but you can use like maximum likelihood estimator or something to be like, well, if I was throwing balls into 1,024 bins at random and I got 700 of them filled, which is taking into account like a collision just like doesn't get noticed, then you can just back it out and be like, oh, okay. So in reality, I probably tried to throw about this many balls in. Does that make sense? So based on CRV, I can estimate the original BRV unless I'm too full.
Basically, would you have basically a confidence interval of how what the range of likely or the true number of neighbors is? Because obviously it's lower bounded by that, but then there would be some with like 90% confidence it's within this range, right?
Yes. So that's what you can do. And actually the lower bounded thing is also useful because in fact, the most useful part of this app is whenever you're talking about people really close to you, because if the app told you there's like 2 people you're around and you're like, no, there are 3, then you just be like, what's wrong with this app? I know the 3 people. You know what I mean? But with the 3 thing, I have no issue. That's probably not going to give me a hash collision. Okay, maybe it will with some very rare probability, like some random user somewhere is like, what's going on with my app? But you know, like if I have 1,024 space, what's the chance that 3 people are going to, you know, hash into the wrong way? It's a minor effect. And at that point, you just assume that maybe someone doesn't have the app installed or something. But now with this thing, it's like, okay, so this is going to be great now up to all of these neighborhood sizes, which are in the hundreds. So then what do you do to handle bigger things? Well, to handle bigger things, what you do is, I'm going to use a different color now. I guess I'll use, since you circled things in green, I'll circle things in blue. What we can do is we can say, hey, let's, for every vertex, not count how many vertices are in the various balls, but let's first have every vertex independently flip a coin with probability P that makes it get picked for counting. Let me make it more readable. So let's make every vertex have a probability P of flipping a coin that means like, count me. Okay, so what I mean by count me is that not every single vertex in the graph has count me selected. And the P might be something like an 1/8. Now, what we'll do is we'll actually make BRV not the set of all vertices at distance less than or equal to R from V, but all count me vertices. Now, what does this do? Remember that I'm doing it independently. So every single vertex gets a random like count me or don't count me. Oh, now the algorithm doesn't start with all B0 just being the V. Now the algorithm starts with the B0 of V is V if V is count me. If V is not count me, it's empty set. Okay, but what this will do is this will actually thin down the sets. So like if the true ball had like, let's say the true ball had 8,000 things inside it. Now the thinned down thing, if P is 1/8, has only 1,000 things inside it. Suddenly when I pass that through the hash function, 1,000 things, I don't know what it's going to be, some math thing. It's probably like some E is involved somewhere because 1,000 is close to 1,024, right? I'll be like, okay, I've occupied, I don't know, 700 or whatever of those things in the CR V. And so I'll say there are probably like 1,000 count me things. And then now I can back out how many original things there are by dividing by P. So the idea was the P thing makes it so that the things I'm counting, my counts are all shrunk down by a factor of P. And then suddenly I'm able to count even when there's like 8,000 things in my ball because I'm only counting 1,000 of them.
So it seems like to me what you're doing, and I guess there's, there's several things going on here. To what extent, like how many of these computations you're doing in parallel for every user or one particular case. Let's just focus on, say, one particular setting. So, or one particular user, let's say. It sounds like basically you don't want to do the most expensive computation at once because you don't have any control over how expensive it might be. And the graph is going to be very imbalanced. So you might be wasting a lot of compute. What you do is you say, okay, let me do an approximate computation both with the hash function and with this flipping thing, because the flipping tells me essentially, it gives you a sense of the discrepancy between the hash method and the true value, and you could kind of dial the p and the hash.
Yes.
So that you kind of you're basically putting bounds on how expensive the true computation is, and
Yes.
you're sort of probing it, right? And so
Yes.
right, and so once you do this a few times, then you'll know, oh, this is how much compute I need to do, and then you can choose the hash size
That's
and
right.
p coordinate. Now, okay, so that's right. Okay, great.
That's
great.
right. That's right. That's
Okay.
exactly right. So the point is that you dial the p, and we dial the p with like 1/8 and then 1/64, and then 1/8 cubed, whatever that is. And so as you keep going, then is that 512? Anyway, it doesn't matter. So as you keep going, like you end up having different values of p help you to estimate like different magnitudes of orders of magnitude of this ball size. But every time you do it, there's only 1024. Every set that you're dragging around is only 1024. 1024 is picked because you can do that with just like binary OR functions.
Yeah.
Like
So
it's
basically
bitwise manipulations.
Right. So I think at the beginning, if you did this naively, you'd have some kind of polynomial complexity where the degree is larger than 1. Here, by I guess p, you'd want these to be, say, powers of 2. Let's say,
so the logarithm comes in. Yes.
Right. So then you would get kind of a logarithm. Yeah. Right. It becomes logarithmic in terms of isolating a good p value. Right. Basically, you. I'm trying to think about it. So I think you'd probably start with. Yeah, right. Okay, here's what you would do. You would choose a very small value of p and keep doubling it, because the smaller the p, the less computation you have to do. And of course, in the case where p is very close to 0, you'd get too few vertices. And then at some point, you increase it enough such that you've kind of, at some kind of capacity, you realize, oh, this is sort of like a good p value. And that's like your threshold, right?
That's basically what we do. We just go the other way around. We start with p equals 1. The only reason is because starting from p equals 1, you'll very accurately find out everybody's local neighborhoods. And then we chop the p down. But it's the same principle as what you said. It's just that,
I see. Yeah. I was thinking about that for a second, but I thought, okay, so I think p equals 1 from one sense made sense, because when you write p equals 1, you know, if assuming this graph is very large, which is what you want to avoid, you're going to get basically everything filled up, and you keep narrowing p until you start getting a little bit of like vacancies, let's say, right?
Yeah.
But I kind of thought, well, with p equals 1, you're doing the most computation also at the start. Whereas I was trying to think, oh, you're trying to save computation, right? So why do you not start from the lowest p? So maybe I think I'm just confused, but why don't you explain? Yeah.
No. I think that's an interesting thought you had there. But the thing is, I actually don't know how close to 0 to start, because when you're on the logarithmic scale, 0 is minus infinity.
Yeah,
so the thing is, like, I don't actually know where to start with a p, because p close to 0, there's lots of things close to 0, like 1 over like a Google, or like, you know what I mean? So the thing is that we started with p equals 1 because when you think of taking logs, that's like starting from 0 and going more and more negative.
Yeah. I see.
And the other reason is because we actually do need the p equals 1, at least for the local neighborhoods, because that's when a user gets like some sense of whether they believe this app or not. And locally, out to like 1,000 people, you can't keep track anyway. So you're like, oh yeah, it seems legit. Like, you know, the number of people who are my immediate neighborhood, their immediate neighborhood, you're not going to get many collisions there. That's going to look pretty good. And then once we see that, you know, you're right, you'll max out. You'll find out that all these sets are like 1024, they're full. But fortunately, like doing the union operation is cheap, because these are 64-bit integers. So actually what we do, when I say 64-bit integers, each set is each C is a set of things, and it's a subset of 0 to 1023. Therefore, it's like 1024 bits. So we can actually represent every C thing as like a bunch of like 64-bit integers, because the bit being 0 or 1 just means that the elements in the set are not. At which point this like union thing is like the vertical bar operator. It's actually a binary OR.
So like 64 just for so 64 bits, right? So that means that you can represent integers. Let's forget about minus signs for a second. So 0. Oh yeah, we don't need these are all positive. So it's 0, 1 all the way to 2 to the whatever 64 minus 1.
That's not actually what I meant. That's not what I meant. What I meant was that every C. I mean, like I see where you're going with that. But what I meant with this was just that every C is actually a subset of 0, 1 to the 1024. Right? Oh, wait, that didn't make any sense at all. But like, no, it's not. That's not true. I mean,
Because
that's
1024, yeah, because
But that's
1024 is
false.
2 to the 10. So I'm just 10 versus 64. I'm just trying to see the connection.
I understand. So I did a bad job of explaining. So what I mean by that is that every single one of these C's is a subset of 0 to 1023. And therefore, I can biject each one of them to something which is, so this is like the power set, right? So each of them is bijected to a 1024 bit, I'll just call it 1024 bits. So every single CRV is a subset of the 1024 options. And
That's
so
right.
it's 1024 bits, and I have 64 bits in an integer. So the number of 64-bit integers I need to store a CRV, a single CRV, is 1024 over 64.
Yep.
Which is some like reasonable number.
Yeah, that's right.
If we could still do math.
Yeah.
I can't anymore. But like
between 10 and 20.
yeah, something like that, right?
Yeah, okay, yeah.
Oh, in that case, it's probably 16 because it's power of 2. Is that actually true?
Oh, that'd be right. Yeah, it's 2 to the 10 divided by 2 to the, wait, so
2
we
to the 10 divided by 2 to the 6. Yeah, divided by 2 to the 6. Divided by 2 to the 6. Yeah, that's 16.
Yeah, okay.
That's 16. Okay, teamwork.
All right, awesome.
So the point is like it's 16 of these like 64-bit ints. So if I want to do the operation like this operation here with the union, well, that's just bitwise-or, right? Like if I have all these like 0, 1.
Ah, nice.
That's super fast. Like the computer does a bitwise-or in like no time flat. So we're basically just dragging around 16 64-bit.
Okay, so for a second, so to take the union of a bunch. What's the statement? To take the union of a set of these binary integers, you do some kind of bitwise-or.
So what I mean is if I have, remember this operation is going to have to take a bunch of CR-1s and union them. But once my representation of it is integer, where I use the bits to represent. Like
that's right. So bitwise-or is, right, as long as at least one set has a 1, then yeah, let's maybe just explain that. Let's maybe go to another slide. So basically, if you have a set, let's make it more general. Let's say let's use little n now for n elements, right? So you're going to get an n. So a subset can be expressed as an n-bit integer.
Yes.
Right, because there are now these sort of n markers, and you just say for each one 0 or 1, depending on not in set or it's in the set, right? So every subset of n possible things is now this n-bit integer because every k here is either a 0 or 1, and there's n of them, so you have 2 to the n, right? And bitwise-or is just the operation of applying bitwise-or. What is this? It's just take 2 n-bit integers and apply or bitwise. So the or operation is basically the max of the 2 integers. So sort of or of, I don't know, I and j would basically be max of I and j. So basically, essentially, in other words, or of 0, 0 is 0, but or of 1, 0 equals or of 0, 1 equals or of 1, 1, which is 1. And to translate that into set theoretic notation, as long as one of the sets has at least a 1, you're going to get a 1, which is exactly what union is, right? You're either in one set or the other. So that's why bitwise-or gives you the union.
Yes. And then so this ends up being really fast because you're just doing a for loop and you're doing bitwise-or on them. So it's actually, you don't have to like for loop through 1024 stuff. Anyway, this is like small optimization.
Yeah, so to summarize, so we just shown that bitwise-or is union of sets, and then basically the complexity is therefore O of let's see, O of n times the number of sets, right? Because for so if you have number of sets here, and then here's all these 1 through n bits that you're looking at, you just kind of go down the columns, right? Which is why you get the number of sets, and then you just go through horizontally through each element. So that's why you get O of n times the number of sets. Yeah.
Yeah.
Okay.
And then we use this like little optimization that in a modern computer, you can do like 64 of them at once. Right? Like
Yeah.
you just tell the CPU, I have these like, they're batched in 64s already. It's like, just go, or these two for me. You know, like if you give it two 64-bit integers, you can just OR them. And in fact, the way C++ is designed and implemented, it probably takes this into account.
Sorry, takes what into account?
It takes into account that like on a modern 64-bit processor, it is already designed to work with 64-bit ints. And so in one go, like it loads the 64-bit int in and another 64-bit in. I don't know.
I see it's already optimized for. Yeah.
But it's already on these 64s. You don't have to do like one at a time. So you
So I'm trying to think. If you did this naively and didn't do this bitwise trick, what would be the complexity of doing all these unions?
Well, you'd have to also, it would be the same. The complexity we're talking about a constant factor improvement, right?
Okay.
So you wouldn't change the complexity, but it's like, I don't need like a for loop that goes through 1,024 things. I need a for loop that goes through 16 things. And each time it's doing something, it's like using all 64 bits of the computer's optimized calculation.
I see. Okay.
It would be sort of like if you had an assembly line that was already with 64 people lined up and 64 people lined up, but you kept giving them work where you just told 2 people to do work. And then, and then the other 63 people just sit there, right?
Yeah. Okay. So yeah, interesting, because of course constants can matter if they're very large.
Yeah.
Right. So I guess maybe the constant isn't so large in this case, but maybe the biggest savings is how optimized the hardware is for certain operations.
That's true. But also for us, since we don't have much money, like a factor of 64 does matter.
Yeah, sure. Exactly. Yeah.
Like because for us, we were doing this on our computers, and if it's taking like 2 minutes in our optimized thing, that's pretty good. Because if you had times 64, you have 128 minutes, which is now harder to do once per hour.
Yeah, indeed. So that's a good lesson. Yeah, constants do matter. Yeah. Okay. But anyways, I thought this was an elegant piece of math. I would not taking unions of sets in my daily things that I do. I didn't actually know this trick off the top of my head. But this is pretty cool. All right.
Oh, cool. Okay.
Right.
Glad you like it.
Okay. Yeah. But sorry, just to maybe we can take a step back and just summarize again the situation. So if we went back, we discussed computing these balls and using p-values. So can you, maybe what I like to summarize from this is, can you compare against sort of end to end? What would be the most naive thing? And then how do you apply this hashing and choosing difference of p end to end in such a way that you can see sort of what the global computation looks like? Yeah,
so I'd say the most naive thing is just using the b's, because that's really just finding out what are the number of vertices at each distance from me. And so if you could, let's imagine we're talking about like a New York situation where the b out at distance 12 might be like 1 million. So with the B thing, right, you might actually end up dragging around something where in your last like 3 iterations, you're taking every single vertex is doing like unions of sets with million things in them.
Okay.
So that's
by the way, this is a tree in sort of the computer science structure, in the sense that every node has like I don't know, like let's say a neighbor attribute where you evaluate the attribute and it just gives you the set of neighbors. Is that okay?
It's an adjacency list. Yes. So what we have is for every single vertex, we can be like, who are the people that are adjacent to me? And that's
so that's a given. Okay. Good. Okay.
So the point is, like, if you did this in the naive way, that would just be the B's. And the most naive thing to do, if you were doing it in New York City, then like as you got R to be 10, 11, or 12, you have these sets which are like million things. Like each of the B's is like million things. And so you end up doing like, for the R equals 10, 11, 12, you're doing like million operation. You're unioning million things.
I see. Yeah, and right. And even with whatever, you are using it. You are using the computational benefits of this bitwise procedure. It's just that if the n and the number of sets are very large, it's still quite expensive. The point is to prune this.
Well, actually, I should be careful. No, you can't even do that. The reason you can't do that at that point is because of space. So remember, we were like, I'm okay using these 16 64-bit integers. I'm okay dragging around 1024 bits per CRV, because that's not that big.
Right. Sorry. Yeah.
If I'm doing it the other way, my sets are from n could be like 1 billion.
That's right. So the point here, you already had this upper bound over here where where n is 1024, right?
Yes, I have it reduced to I have it reduced to 1024, and
Right.
the reason why you can't do it with the B's is because you still have Siberia in your graph, and you're not taking into account the fact that, well, you wouldn't know. Like, how would you know this is New York? How do you know that's Siberia? You haven't thought about that yet.
Here's the key point. The point is that the subset we need to know in advance that the subset is bounded. The number of elements has to be upper bounded by n in order to have this correspondence to begin with, right?
Yes.
Because if there were an unbounded number of elements, you'd have to put in zeros, pad it with an arbitrarily large number of zeros, possibly, right?
Yes,
so
and that becomes really expensive.
Exactly, exactly.
Because then that gets really expensive. So the reason why ours worked is because we actually shrunk it down first. So then if you think about how much work you're doing, well, with ours, then we actually will never do a million things. We'll never do these like million set unions. We only do like 1,000 set unions, and we probably have to do like 3 different levels of P to get there. Because the thing is that our levels of P go from 1/8 to 1/64 to 1/512.
Okay.
And at each level of P, we get approximate measurements that are about right as long as our hash function, as long as the things that we actually count are maybe up to like 1,000 to 2,000-ish. So what I'm saying is that like up to, what I'm saying is like up to like, if I have like 2,000 things I'm counting, that's after the P sparsification. If I've already sparsified down by my P and I have like 2,000 things, maybe not 2,000, but like around 1,000 I'm comfortable with. But like if I've got 1,000 things that I'm putting in through this hash function, I'm pretty confident that I'm not going to fill all 1,024 hash spots. I'm pretty confident that whatever I fill, I'll be able to back out with maximum likelihood and get something close. But if that corresponds to P being 1/512, basically at P being 1/512, I can already count things up to 1,000. That lets me count things up to 500,000.
Sorry, that's
So what I'm saying is, if the true size of a ball is up to 500,000, when I do P being 1/512, I'll be able to pretty accurately estimate how big that ball was.
A million divided by 512 is roughly.
I said the wrong thing. I mean, like if it's 500,000. So if it's like 500,000, if I have 500,000 things, if my ball size is 500,000,
so then you're roughly 1,000. Right, exactly.
1,000 hashing into 1,023 spots is going to give me something with that E factor. It'll be like maybe 700-ish, and then I'll reverse it back with maximum likelihood. I'll be about right.
Right.
So what I mean is, like in the New York scenario, once I've done P being 1/512, I'm already doing pretty well. Maybe I need to do a 4th level, but that's what I mean by logarithmic.
Sure. Yeah, but I think this is where no. Okay, I think I see. Okay, I think this now that we've talked about this again, I think I'm now more clear about why you were able to start with the P equals 1 and work down. It's because of this hash function already sets this upper limit of n.
Yes.
So even with all the million nodes, you could still apply this trick.
Yes.
Yeah, I get it now. Okay, so maybe let's just summarize this. Let me go to another slide. So basically, if you have whatever 500K, let's just say they're just nodes, right? And of course, if you sort of hash to this set of 1,024 elements, there's a very high probability that's just going to get filled up, right? So what you do is then you, let's say P equals 1/2, right? And then you're going to get 250K. Then you just keep on going until you get roughly 1,000K, right? Once P is roughly 1/512, right? And
you mean 1K?
Oh, sorry, 1K, sorry, right? And this is now finally you're going to get some sparsity, or you're going to get some.
You're not going to be overfull. That's the idea.
Yeah. You're not filled up, right? And so basically, you'll be within a ball. Well, okay. So it depends on how good your estimates are. I can see yourself being off by say maybe a factor of 2, because right before the 1/512, you had roughly 2K, and here twice as many elements trying to fill.
Yeah, you probably filled pretty heavy there. Yeah.
You're saying even with double, it's likely to get filled. I mean, I can imagine maybe there might be one guy that's missing, but you said that's also unlikely.
I don't expect it to be full, but I expect it to be so full that you don't know whether it's 2,000 or 3,000.
Got it. Okay. So so there is some kind of statistical constants to be worked out here, but basically with the right threshold, you'll know whether you're in the 1K or 2K case.
Right.
Okay.
And actually, the reason we cut our P not by a factor of 2 every time, but by a factor of 8 every time, is because you see, right here you saw, like, if you throw 1,000 things into this 0 to 1023, we probably can get it. But if you actually threw 128 things in there, you'd probably get it too. You'd probably get a pretty good estimate too. The only time you have a bad estimate is if your P is so small that you only try to throw 2 things in there.
That's right.
Now you count 2 things, that's good. But like, you have too much variance in the true value times P gave you a 2. Like that one has the error. Does this sort of make sense? I'm like, there's 2 ways that you can get the error. One way you can get the error is from this random sampling of every vertex with a probability P. And if it was too low of a probability, there's noise in, did I pick 2 or 3? And that's like a 50% difference, by the way, because eventually we're going to undo the P effect.
That's
so
right.
you want that's pretty tight. So you want the post-P sparsification to be not too small of a number. But you also want it to be not too big of a number. So you want it to be some number, I don't know, like 100 to 1,000, or probably even like 20 to 1,000, something like this. And so I just need that, no matter what the true original number is, as I go and keep hacking the P down by some factors, at some point I land inside this sweet spot range.
Right. And then the question becomes,
yeah.
And then the question, so then my question was basically, once you're in that sweet spot range, how much have you narrowed? What is the error in the true value, right? Is it really actually 10% as opposed to, say, 50%?
Yeah, it's probably something around 10%. I mean, that's why I was saying this thing of like, and by the way, it's probably less than 10%. We could actually work this out if we sat down. But like the thing is that it's because one source of that error would be if you made the P jump too fast, and at some point your P times the true value, if the expected value of that was like 0.6, and then you either get 0 or 1, that would be bad news. Like you'd have like a lot of error on that, because like these are integers. Whatever you actually get is an integer. But since I said we eventually want to drop it until the expected value is at least 100, if the expected value is at least 100, I'm not going to get too far off.
Yeah, my guess is
independent.
My guess is that there is a relationship between how quickly to drop the p-value and the size of the number of bins, such that by optimizing those two, you will get an error range within some desired range, right?
Yes. Yeah. Yes, that's exactly right. And we just didn't bother to do that because it was like, it worked well enough for us. And that's not the main problem we were trying to solve. But what you just isolated on is exactly right. It's like, if we made more things than the 1023, then we could make the P drop faster. If we made less things than the 1023, we can make the P drop slower.
Right.
But these two both work together because, like, well, in the end of the day, how much work did I have to do? If my P typically has to drop like 3 times to handle like up to 500,000 nodes in my neighborhood, well, how much have I saved this way? I've just done like 1,000 node, like 1,000 set unions. Sorry, 1,000 vertex, 1,000 element set unions, and I've done it 3 times. I've done like 3 rounds through, so it's like 3,000, if that makes sense, which is a lot better than doing a 500,000 union. Does that make sense? It's like, because the other one, I have some things that involve like unions of sets with 500,000 things in there.
Right.
And so instead of having to deal with the 500,000 stuff, I do like 3 things, three rounds through each time only with 1,000. And 3,000 is a lot less than 500,000. Now, how to optimize the two, you could probably do better than what we've done, actually.
Yeah, so I think what I said earlier was it wasn't quite right, but it was the same idea in terms of like finding, using these random methods to sort of probe the true complexity of the computation. But actually each step of the computation is equally expensive because of this fixed bucket size. So I was a little bit wrong on the last part, but so that's why it doesn't matter whether you start with P equals 0 or P equals 1, but from a computational perspective, but from a variance perspective, that's why you started at 1. And it makes more sense now. Yes.
And I can also say, I think the reason why we were happy with 1,023 is because that's only 16 of these 64-bit numbers. 16 is not a big deal. So I was like, like if we should have done it with 4 of them instead, like, what are we going to do? Like, there's not much space between 16 and 1 anyway. So that's why 1,023 seemed to be okay. Yeah, but that's what we did. So
that's great. That's great. I mean, I definitely learned a lot. You said this was trivial. I didn't think it was trivial at all. This is, it's maybe, maybe you don't need necessarily a PhD to understand it, but it still requires some good ideas.
Oh, yeah, that's good. That's why I work with smart people. Actually, the idea of sparsifying the P, that was Brandon's idea. So that was a high school student. So it's always good to surround yourself with very smart high school students.
Okay, great. Well, this was awesome. is there anything we didn't cover that you wanted to discuss?
No, I think this was terrific.
Okay, awesome. All right, Po, well, this was really great to have you here and explain the mathematics behind NOVID. It was great catching up with you and learning new things, but also I think this is so many birds with one stone, right? Because you're an educator, and obviously we've are trying to educate people about this, but also showing how math can be used in the real world. I think that's also very valuable, and this is definitely math in action.
Well, terrific. Thank you. And Tim, thanks for organizing this this podcast. I actually think this is quite an interesting format you have here. I have done a lot of different podcast interviews before, but none of them quite have gone this way where we start discussing things with another person about math on a board. So good move.
All right, great. Well, thank you, Po.
Okay, take care.
All right.
See you next time.